Hello everyone, thanks for listening. I wanted to do a video that described to everybody what I see happening within my design, and so that's what this video is going to be about. So basically it's a design for a new electric motor, and similar to an AC motor that has three phases. The device itself also has three phases. However, where the wires of an AC motor or the circuits are simple wires, the circuits within my motor are comprised of capacitors, and these capacitors move direct current through circuits. So if you could use capacitors as circuits to a motor, then it affords you the ability to be able to access the circuit in order to have a closed system oscillate with another closed system. And that's the premise of the device is that I'm not creating free energy. I'm simply unlocking what is already there. So to understand that statement, one has to go to Maxwell's equations, and these equations changed our physical understanding of electromagnetism and the way our world itself works. But within those equations, they determined fields and locations of fields that existed around circuits, and he found that within capacitor plates there existed an electric field. However, this field would mean that there should be an electrical current, but this current was never found, and if Ampere's law was correct, it meant that it must be there. So within the equations, a displacement current was created, and this displacement current was an equal and opposite force inside of a circuit, inside of a simple wire. And so if we create phases to an electric motor that were comprised of capacitors, and these capacitors were essentially portions of track, then every time that we created a current that had an equal and opposite force, if we found a means to move that force onto a separate circuit, then the force that was preventing it from moving forward would be moving forward on its own circuit. And this has the same effect as trying to walk up a hill versus trying to walk down a hill. So now by having two circuits in oscillation of each other, we have two waves that are oscillating against each other, but we need to try to harness that, and we do that by trying to select the producing aspect of that wave. And what I mean by that is that every wave, every oscillation has a positive and negative amount, a positive and negative current that is created during its process around. And as it moves around, we can chart that on an oscilloscope, and we see the top half and bottom half. So by having two circuits, we simply are selecting the producing aspect of that wave, of that circuit, from opposite ends. And this would be the concept of choosing the present moment of a forward moving hot wave and a backward moving cold wave, and recombined to have one circuit that is constantly producing. And so the signals and the timing of the oscillations and switching are going to be very crucial in figuring out the design. However, no different than your distributor cap works on a combustion engine and how important of a role it plays. We're dealing with two closed systems that the timing can be predicted and perfected. So the goal of the device is going to be to produce some sort of useful task that would allow it to unlock that potential. And that useful task is going to be alternating direct current. And so we do that by combining both alternating and direct current attributes into a device that would mechanically alternate direct current so that we could allow that direct current to be transformed. And the transforming of that direct current through this device would essentially become a wireless DC current. So to start the device, we're going to attempt to build circuits out of capacitors. However, direct current doesn't pass through capacitors where alternating current does. And this is caused from the electrons' movement within each different current, where in alternating current, the current moves from one side to another, and in direct current, the field is consistently forward. And so by switching direct current circuits open and closed, this oscillation shows up similar to the oscillation of an alternating current on an oscilloscope, and this would be the means to allow direct current to actually pass through the capacitors by pulsating the circuits themselves. So each portion of the tracks that we're creating are made with 3-electrode capacitors and a magnetron anode. And so the 3-electrode capacitor essentially simply moves potential inside and out and creating reactions within. And the magnetron anode is used to harness the displacement current that is created between every reaction. So the capacitor sets are created with 3 electrodes. We have 2 cathodes and 1 anode, and preferably the anode is copper, and the electrodes or the cathodes themselves are electroplated magnetic materials, and essentially the cathodes are going to become the magnetic core of a transformer. So to create this transformer, we need to have inducting coils wrapped around the cathodes themselves, and so the size and amount of these wraps and which way they go is going to be something that is going to need to be researched. But the intent is going to be to oscillate signals between inducting coils fast enough in order to be able to create an oscillation where you harness higher energies out of a direct current. So inducting coils send oscillating signals inside and out of the individual anode, and we're basically moving potential from one side to another. Now, the 3 electrodes essentially are the 3 bodies in the law of thermodynamics, and this basically says that 3 energies share between each other and essentially will reach an equilibrium between them. And this is the force that we're fighting, in that the 3 electrodes will have a normal resting state, and by using or by pushing energies through them, we're moving them from their normal state, and they'll force it back again. And this is part of the oscillation that happens, and it's very similar to what we find in heat pumps sort of effect, where we push from one side to another with chambers. And so essentially 3 electrodes store their energy inside 2 chambers, and we move that energy potential between the 2 chambers themselves. So obviously the 2 chambers are the dielectric material between the electrodes, and material itself is either solid state or liquid electrolyte material, but essentially it's what moves the potential between the 2, and it would probably contain some sort of piezo or pyroelectric type materials within it. The wide-ranging materials for dielectrics are just too wide to be specific, and I do have some ideas as to the way to approach it, but it's not something that I care to talk about. But essentially, we're just looking to find a means to transfer the electrons very quickly, and the charges will come back very quickly. We need to move it with as little resistance as possible. So an often overlooked part of any capacitor or battery is the separator. And so in the capacitor magnetron sets, the separator I'm using is going to be made of graphene. And in recent years, they have been used for these type of applications. And they've found that the electrons move through very, very quickly. And that's the type of characteristic that would be ideal in this situation. Along with that, researchers have found that when electrons move through graphene, they move through as if they have no weight, and that has physicists all around very confused as to what and what that means. And so basically that property is gonna take effect within the device and will take place at the same time some other parts will exist. So as these oscillating signals come in through the cathodes, they basically transform back to each other. And where a typical transformer, the iron core is laminated, and in order to get rid of the heat, we're actually using the dielectrics as a means to use that heat. And using pyroelectric materials, we can transfer the electric charge quite quickly and easily. And that's one of the major effects that would happen with the transforming of the inducting coils, is the recycling of the heat that would be created, as well as the start of original signals within the device. So then this 3-electrode capacitor that has signals introduced to it is inserted into a typical magnetron, a cavity magnetron. And essentially what happens is, in the operation of the capacitor, the heat that is created is sent out to the outside cathode of the capacitor set. And that cathode is actually the interior cathode of the magnetron. And where a typical magnetron has its cathode with a filament to heat, that filament is actually replaced either in full or in part through the operation of the capacitor set. And this is what consumes any heat generated and allows for the unlocking of a displacement current onto a separate cycle, which really would change electrical theory as we know it, because if the equal and opposite force that was contained in a circuit was on its own, and those two circuits would be able to be recombined, the power behind that would be incredible. So far we've talked about the electrodes that would exist within the capacitor magnetron sets and our want to put them into circuits, but we haven't discussed the means to be able to transfer their signals from one cell to another. And typically in our computer age today, switching has been performed by transistors. However, in days past, our computers were composed of vacuum tubes. And vacuum tubes offer a very unique approach that can be taken with the machine. And so a vacuum tube is just basically something that's moving a charge in a vacuum. And it could be very simple as a diode where they're just moving the charge, or it could be a little bit more complicated with grids and screens that are actually filtering signals. And these sorts of things are used in music amplifiers nowadays. Musicians swear by them. Digital ones simply don't cut it. And so in a vacuum tube, we're able to both filter the signal or wave, but we're also able to filter the direct current power that flows from electrode to electrode. And so we're rectifying signals so that signals are able to show up on one side of a line, and we use the direct current to heat the opposing electrodes. And with this, we would get an oscillation between charging a plate and heating a cathode from opposing ends. So basically, with everything I've explained up to now, I'm hoping you can see how this capacitor set comes together. We have two capacitor magnetron sets that are connected together with a vacuum tube, and this vacuum tube filters signals from either side, and as these signals come through, the signals are rectified. The direct current is used to heat or charge opposing vacuum tubes, and the signals that come through from that are sent either onto the capacitor anode, or the displacement current is sent onto the magnetron anode. So the displacement current isn't just going to want to go onto the magnetron set. We have to provide a means for it to be able to get there easily. And so within circuits, the electrons themselves have a northward or southward rotation where they're moving one way or another. And this is what actually causes the resistance in a circuit. And this is what causes the ability for alternating current to actually have all of its benefits, is the fact that the electrons themselves have an orbital path and they move one way or another, bouncing off of each other as they rotate in that circuit. And so this is what we're going to be seeking to separate with every reaction. And we're going to do that by using magnetics within each circuit that we're creating. So within the anode of the capacitor set, we will have a magnet placed inside that is directing a polarity in one rotation, and we'll have a magnet within the magnetron set directing the magnetic polarity in opposing directions. And so magnets within anodes are well documented. This is how magnetrons themselves work. The magnets amplify the rotation of the electrons within. And so basically we're creating two circuits within one phase of power, but we're separating the electrons so that in one circuit they're rotating in one direction, and in the opposing circuit they are rotating in the other direction. And through the use of magnets, we're essentially creating hyperloops. And so the concept is that by moving the energy fast enough, that we'll be able to unlock the electric field on displacement current, which is a time varying field, and have it match up with the time varying of the capacitors, so that every time the capacitors are fully charged, the switching happens, and the switching then harnesses the potential from that capacitor. And as that time varies, it gives time for the other capacitor to charge. And this oscillation is what we are harnessing. So this concept is really important to understand in the design of the device, in that capacitors vary their energy in time, meaning that they need to recharge and then they discharge and recharge and discharge, and this time is their time varying. Displacement current is an electric field that exists as a time varying field, meaning that it shows up between the plates and it doesn't, and it shows up and it doesn't. So what we're attempting to do is to match up the two fields so that the electric current, the displacement current that's creating that field, lines up with the capacitor plates when the capacitors are charging and recharging. And this is going to be the means to unlocking the displacement current onto a separate circuit. And so when we combine the two currents and their directional rotation back again, this is the action that is going to change electrical theory, because we are mechanically alternating direct current. So if we go back to the beginning where we talked about the attributes of AC and DC current, and mainly being that DC cannot pass through capacitors or be transformed, and AC can. And so by setting up the system in the manner that we're doing, we're putting DC current through capacitors and affecting their actual rotation, and putting them into two separate rotational circuits. And when we recombine them, the current is moving in opposite directions, but the electrons themselves are moving all in right hand sort of rotations to that current. So far we've discussed the circuits and how they are separating the displacement and electrical current from each other and creating heating and cooling cycles. But we haven't talked about an input signal, the inducting coils that are wrapped around the cathodes and that feed the grids for the vacuum tubes for their specific wave pattern don't have an input signal, and that's where a Roden coil comes into play. As every electrical motor or AC motor has a coil wrapped around it in order to move the electrical current around the simple wires, the device here also is going to require a coil to be wrapped around it, and that's the Roden coil. And over the last so many years, the Roden coil has been researched by independent sort of people, and people have been finding some interesting things with it, but it hasn't gone very far since that. It was promised to provide so many applications, but nobody actually took it any further than that, and it kind of fell aside. And I kind of attribute that a lot to the fact that the people that were looking at it never raised any money and weren't able to. And maybe that's partly because of the claims that it was making and the fact that there was no clear direction as to how it could help and what it could do. Now I believe that to be a different case, because with the design of my circuits that are seeking to move displacement current and create two cycles, I believe that the Roden coil is going to be the means to introduce that signal into the circuits. And the Roden coil itself, in the test that they've done, when they introduce a low signal, an amplified signal through the device, and they have a magnet within it, it just throws that magnet out. I mean, the field that is created is so intense. And if you could imagine that coil wrapped around these circuits, we're going to have a magnetic field that is both inside and out of the magnetic fields of the three phases of circuits that form the electric motor. So where the circuits connect, the three phases connect at the top and bottom, becomes a switching point. And this switching point is, like I said earlier, is the part that alternates the currents and gets recombined and gets put into two rings that are carrying the individual charges, moving the electrons in their own particular rotation. And these rings and these circuits are all still part of the same circuit. And the magnetic field of the Roden coil itself will both be inside and out of the magnetic field of those circuits. So I've explained a substantial amount up to now, and I think I'm going to leave some parts to myself. But if you understand electrical theory, then the pieces that I've explained should be enough for you to begin to question the basics of what we've been taught. In electrical theory, resistance exists as both matter's resistance to flow from one electrode to another, and it also exists in matter's restriction to flow in a circuit, and that's known as impedance in an AC circuit. And so, within my design, I have both of those at play, but I believe that mine solves for the heat that would normally be so detrimental to AC or DC circuits, and uses it as a means for supplying heat to a magnetron set. And that magnetron that's used in microwaves essentially becomes not a cold fusion but a cold current to my circuit. Individually, most of the other components are substantially known about. Iron cores with magnets and inducting coils around represent speakers, with the dielectrics being the diaphragm, and vacuum tubes changing signals around represents amplifiers, and the entire setup itself is wired together like an AC motor with the mechanical alteration of the electrons themselves. And so essentially we have speakers that are pointed at amplifiers that are connected together similar to an AC motor. And although the concept of being able to get free energy from a circuit would seem impossible, researchers have recently found that they are able to do just that. Using graphene within a circuit, they were able to generate more electricity from the movement of the graphene. And although I'm using graphene within my circuit and I have a lot of other parts at play, the parts that I have at play allow me to extrapolate I believe something substantially greater than simple batteries. So I hope you can appreciate the amount of work that's gone into this and the amount of work that I'll still need to do. But that means that in the coming weeks, I'm going to be having a crowdfunding campaign that's going to help me raise the funds in order to try to build this device. And so if you're hearing this now, I ask that you like, share, and subscribe. And please leave a comment so that I could use this video for that campaign. But in the meantime, I realize that money's tight for everybody these days, and so with that, you can probably just simply ask Elon to help me build it. If there's anybody that has the money, and if there's anybody that's gonna understand it, it's him.